So to do this question, what we need to do is we need to actually stage it, because the ball bearing, it behaves differently when it is above the oil and below the oil. So in the first stage, this is stage 1. It is actually above the oil. And in the second stage, stage 2, it is actually inside the oil. So let's consider stage 1, above the oil. We're going to make another assumption. We are going to assume that air resistance is negligible. Alright, so how do we analyze the problem? To draw the VT graph, you must remember that it's not just looking at the velocity. The gradient of the VT graph is actually the acceleration. So often to do all these questions, what we need to do is we start by analyzing the gradient, and which is actually the acceleration, and therefore what we will look at is actually the resultant force acting on the body. So this is why we often draw the free body diagram. And since we assume that air resistance is negligible, if I draw the free body diagram, I find that there is only the weight acting on it, mg. So by Newton's second law, I'm going to use short form. Do write this out in exam and spell it out. Okay, then we know that Newton's second law says that the sum of force acting on the body is equals to ma. Alright, now if I'm going to take downwards as positive, then what we will have is ma, the sum of force is actually equals to mg, and since it's positive as downwards, my a is actually equals to g, and it's positive g. Alright, and what we note is that the acceleration is actually constant. So if I were to draw the VT graph in the first stage, so let me just change the color of my pen, and I draw the VT graph. Okay, so let me just draw my VT graph. And the gradient represents the acceleration. Then what I would have is it starts from rest, and therefore what I will have is I will have a straight line graph, okay, where the acceleration, which is the gradient, is equals to g. And I'm going to go label this, and this is actually t1, and of course this is 0. Okay, so this is stage 1 when the ball is actually just above the oil. Okay, now in stage 2, so I'm going to analyze stage 2 now. Okay, so stage 2, okay, when it enters into the oil. Alright, remember there are 2 cases for us to consider. So our first case, case 1, case A, according to the question, my drag force, I'm going to call Fd, is actually greater than the weight of the ball. Okay, so let's first ask ourselves, why will the drag force be bigger than mg? Okay, we know that earlier on from our lecture notes, the drag force actually increases with speed. Okay, be it turbulent flow or laminar flow, it's going to increase with speed. For it to be much greater than g, therefore we can actually conclude that it actually enters at high speed. Okay, alright, and if we were to draw a free body diagram for the ball inside the oil, so when the ball is inside the oil, then what we will see is that we have our weight still, mg, but our drag force now is actually larger than the weight. Okay, so it's traveling at v. Alright, but this diagram also tells me that my net force is upwards, because the net force is actually the drag force subtracted with the weight subtracted from it, and this will mean that my net acceleration is upwards. Okay, so taking downwards as positive again, so we will see that our net force is actually negative because it is pointing upwards. Now, it's for us to complete the graph, we need to know how this net force is going to vary. Now, because your net force is also in opposite direction to the velocity, you will note that therefore what will happen to the object is that the object will actually slow down, okay, and the speed will actually decreases, okay, and as the speed decreases, this means my drag force will decrease, and it will keep decreasing as my speed decreases all the way until the magnitude of my drag force is equals to the magnitude of the weight. And when that happens, then your net force is going to be 0, and then it will reach terminal velocity because the acceleration is equals to 0. So let's put this on our diagram and complete this diagram. I'm going to copy it here. So let me just click this picture, okay, and copy, okay, and put it down here and complete our diagram. Oops, okay, paste the image. All right, and let me fill this up. Okay, so this is our VT graph. All right, so what is going to happen next? Remember, we have taken downwards as positive, and initially as it drops into the oil, my net acceleration is upwards. So it's actually going, the gradient is going to turn negative. So I need a negative gradient. Okay, so it's going to be a negative gradient. Now, not only is it a negative gradient, subsequently my drag force is going to reduce in magnitude, and this means my gradient magnitude is going to actually decrease as well. So the slope will get gentler and gentler and gentler all the way until my net force is 0 and my acceleration is going to hit 0. This means it would have reached terminal velocity. So if I continue my graph, then it's going to reach terminal velocity. This should be a straight line, smooth straight line. Okay, and your graph will look something like this. Okay, so where this is the terminal velocity. So this part of the motion, okay, your net force is negative, so your acceleration is negative, your gradient is negative, and the magnitude is actually decreasing, so it's getting gentler, and eventually it hits a point where it hits terminal velocity. So this is the part where the net force is equals to 0, so the acceleration is 0 and the gradient is 0. So this is for case A, where my drag force is actually going to, when it enters the oil, is actually going to be bigger than the weight. Okay, so let's look at what about case B. I'm going to bring this down. Okay, so we're going to look at case B, and in case B, what we are looking at is we are looking at the case where my drag force is is less than the weight when it enters. So again, we know our drag force is actually dependent on the velocity. Okay, velocity v. Okay, so as it enters, this means as it enters into the oil, it enters at low speed, so that the drag force is actually small. And again, we're going to draw a free body diagram for the oil. Okay, because that will allow us, for the ball bearing, because that will allow us to analyze the net force acting on the ball bearing. So we've got our mg again. Okay, but in this case, my drag force is very small. Alright, so my drag force is small, and if you look at the diagram, you'll be able to tell, therefore, that my net force is acting downwards, and hence my net acceleration, my acceleration is of the object as it's going in, okay, is also acting downwards. And since we have taken downwards as positive, this means the subsequent acceleration is actually positive as well. Okay. Then subsequently what happens? Now because the acceleration is in the same direction as the velocity, so what we can see is the object is going to speed up. As it speeds up, the speed increases, the magnitude of my drag force is going to increase. Now it's going to increase until when? It's going to keep increasing until this drag force is going to be equals in magnitude to the weight. And when that happens, my net force acting on the object is going to be 0. And hence, the acceleration of the object will be 0. And the velocity becomes constant. And we would know that, therefore, the object has now reached terminal velocity. Okay, so we're going to represent that on our graph. So I'm again going to clip my graph from above and continue this graph. So let's copy this, okay, and let's bring it down. Let's bring the image down and continue the next stage of our motion. In our next stage of our motion, our acceleration, what it's going to do is actually it's going to be still positive, all right? So it's actually still going to be increasing in speed, but except it's not going to increase as fast, so the gradient will not be as steep as before. So it's going to go gentler and gentler and gentler, eventually to the point it's going to reach terminal velocity. So this is the point where it reaches terminal velocity. Let me change my shape a little. So this is the point where it hits terminal velocity. Let me try and make it nicer, this shape here, okay, so that the graph will look nicer. So this is the point where it hits. Oops, let me go to make it a solid line. Okay, and then so this is the point where it hits terminal velocity. So this is my terminal velocity. And if you want to label, this is A, still accelerating, and it is downwards, but it's less than G, okay, because the net force is less than mg because of the presence of drag force. And eventually, this is the point where my drag force is subsequently going to be equals to the weight. So my A is equals to 0, all right? And this is where I have terminal velocity, okay? So these are the two cases and the two graphs that you get. For case A, where the oil is going to enter at high speed and the drag force is larger than the weight, and case B, where the drag force is less than the weight. Okay, so that's our answer.